To understand probabilities, it helps to have some definitions first. So we're going to look at probabilities as they pertain to statistics. So let's get a few definitions first. First off is, what is an experiment? An experiment is an activity where the actual known results, are not sure which one will happen. In other words, you've got some things you know normally happens when you do an activity, but you don't know which one actually will happen. So you have these actual known results. I should have said results in here, but are not sure which one will happen. So in other words, flipping a coin is a known activity. You know you're going to get a head or a tail. You just don't know which one you're going to get. An outcome of an experiment is one of the known results, a known result. Now, when I say that, you might not have all the results. You may not know every single result that could possibly happen, but in most cases, we normally know what activities could happen in an experiment. An event is a collection of a certain number of known results, of outcomes. Of certain outcomes. So in other words, you want to say, I'm going to roll a die, and I only care about getting an even number. My event would be getting an even number, and I would have my outcomes would be the 2, the 4, and the 6. A sample space is a listing of all possible outcomes of an experiment. So we know what those outcomes are, and we can list them all. If you list them all, it makes probabilities much simpler because you are just going to be counting in most cases. And then if we have a sample space, we can also have an event space, and that's just a collection, a listing of the outcomes of an event. So those are basic definitions, and we're going to be using these basic definitions of probabilities throughout the rest of the discussion of probabilities. And those are our basic definitions. Now we can talk about what we call experimental probabilities. Experimental probabilities are, you're going to repeat an experiment a certain number of times. We'll call it n times. You're going to count how often an event happens. And then we can actually find the probability of that event. So the probability of an event is the number of times the event happens over the number of times the experiment's done. So over n, we'll just call it n. It's way easier than trying to write all that out. So you're going to do an experiment. You're going to see how often does it take to have that happen. And then you're going to divide by n to find out what that probability is. Before we go too far into doing an example of this, I want to talk about the law of large numbers. The law of large numbers says, and before we do that, I want to go back and just mention that you can also think of this probability as the relative frequency of an event. So another way to think of probability is the relative frequency of an event. And what we mean by that is, again, it's the number of ways the frequency of the event happens divided by n. And that can help us with the law of large numbers. The law of large numbers says that the relative frequency approaches the true probability as n gets larger and larger. So in other words, if you repeat the experiment 5 times, you're going to get a probability, an approximate probability, and your relative frequency. If you do it 100 times, you get a slightly different answer, most likely. If you do it 1,000 times, you get even probably a slightly different answer. And as you keep increasing that, you're going to go towards the true probability. Now let's go ahead and do an example where we're doing some probabilities, show you kind of what's happening here. So we have an experiment where I rolled a die 120 times and I counted how often each side comes up. So in this case, my frequency would be the 91. How often did I do the experiment divided by the 120, or how many times did I see one come up, divided by the 120, which is how many times I did the experiment. So I divide the number of times I saw the one come up by how many times did I repeat the experiment, and I get about 0.76. I can do the same thing with all the rest of these. I saw a 2 come up 6 times, so it'd be 6 divided by 120. And that is actually equal to 0.05. I saw a 3 come up 5 times, so it's 5 divided by 120. And that's approximately 0.04. I can do 8 divided by 120, and that's roughly 0.07. And then I can do the 5 divided by 120. I'm sorry, not the 5, the 7 divided by 120. The number 5 came up 7 times. And that's 0.05 or 0.06. And then 3 divided by 120. And that's approximately 0.025. And actually, that wasn't approximately, that's an exact. And so we get these probabilities, and so I can now actually tell you the probability of getting a 1 on this die I rolled is approximately 0.76. If I were to repeat the experiment more and more and more times, I would get a better approximation to what the true probability really is. But it looks like, because 120 is not too bad, it looks like it's about 3/4 of the time it came up with a number 1. And I can do all the other sides too if I wanted to. So let's go do another example. Let's roll a die 400 times and count how often each side comes up. So in this case, my n is 400 because I repeated the experiment 400 times. We're going to have 51 divided by 400. And that is 0.13, let's call it. And then we can do the same with 70 divided by 400. And that is approximately 0.18, sorry. And then 67 divided by 400. And that is approximately 0.117. Then 73 divided by 400. That's 0.18. 66 divided by 400. 0.17. And 69 divided by 400 is about 0.17 also. And so these are known as experimental probabilities because I actually did the experiment, counted how often I saw a side come up, and actually calculated these probabilities. Notice they're not all the same value. But again, if I were to repeat this experiment more and more times, these would slowly approach what the true probabilities really are. I do want to point out that these probabilities of each of these sides are roughly around the same value. Whereas these, when we did this other die, none of them were near the same value. We had 0.76 and then 0.05, 0.04, 0.07, 0.06, and 0.025. These are actually pretty close. Actually, we'll call this one 3. These were all kind of close to the same value, but at least some of these, but not this first one. This first one's way far away. Now, with a die, I would expect them all to be about the same. I would expect all of these sides to be about the same, like it was on this die. Looking at this die, they're all about the same, and that's what I would expect to happen. So since this die got me what I expect to happen, I would say that this die seems to be fair. However, since the probabilities are all around the same value. However, this first die I was looking at, this does not seem to be a fair die. This probability is way far away from the rest of them. So this die does not seem to be fair, since the probability of 1 is very different than the other sides. And that's how we actually tell if a die is fair or not, is we actually have to do the experiment, see if we get similar probabilities. If we do, then we can say the die is most likely fair. But this one, we would say the die is most likely not fair.